2026 is on the way. And then Chinese New Year. More importantly, you will have a 2 full months winter section. Okay, so good things are ahead of you. Okay, and I hope you are well planned for the coming winter section and have a very very happy time for your winter sections. And I want to remind you that you probably won't have such a good opportunity in the future because the time for being a student for you is coming to the end. After all, you are undergraduate students, and this is your junior year. All right, so less than 2 years to go before you graduate from college. Of course, you can go to graduate school and pursue further training for additional 2 years. But after that, I think you still have to go to find a job and stop your career. So if that's the case, you won't have summer and winter sections annually. All right, okay, so you don't have that many winter and summer section left because the time for being a student is coming to an end. All right, so cherish this winter and summer sections. Okay, in the previous lecture, we introduced phase margin and gain margin to shed some light on the impact of phase margin and to help us understand more about the impact of phase margin on the performance of the system and in particular stability, or more specifically relative stability. Let's look into its relationship to the damping ratio. Okay, we all know that damping ratio shift is a very important parameters for second order system. So this is a closed loop feedback system with a loop transfer function look like this. And you know that is the transfer function for this feedback control system is this, which is apparently a standard second order system. Now, remember, when studying gain margin and phase margin, the focus is on the loop transfer function, not this one, okay, but loop transfer function. All right. Since we are in the frequency domain, I replace x by j omega, and this loop transfer function can be rewritten as this. And right now, because my goal is to determine phase margin. So the first thing I need to do is to determine the gain crossover frequency. That is, if this is GH, I want to know the frequency that make the frequency where the magnitude of GH is 1, okay? And therefore, its dB value is 0, okay? So let's take the magnitude of this loop transfer function, and it will look like this, all right? And this has to be 1 if omega is indeed the gain crossover frequency. If this is the 1, if this ratio is 1, then the numerator has to be the same as the denominator, all right? So if that is the case, then we will have this equality, all right? By knowing the fact that this has to be equal to this. Remember that when going here for please be noted that when going from this to this, what I did is I take the square of the numerator, which gave me this. And if I take the square of the denominator, this is what I end up with. And because they has to be the same, so the difference has to be 0. All right. Now, by solving this, by finding the roots of this polynomial, okay, why is it a second order polynomial? Because again, I divide everything by omega squared, and then I treat omega c over omega n squared as, for example, x. Then this equation will look like a second order polynomial whose root can be readily determined. And that is what I have. All right. Now, the phase margin by definition is this. Where does 180 degree come from? Because it, by definition, it is the difference. I'm sorry. Phase margin is the difference between the real phase and minus 100 degree. So if you subtract minus 100 degree, what you do is the same as acting 180 degree. Where does this two term come from? It comes directly from here, all right? J omega result in minus 90 degree. And the phase angle of this term is this. The reason why we have a minus sign here is this term is located in the denominator, appear in the denominator. Remember, okay, I reviewed this equality. That is, if you have complex number a plus jb, let's say its angle is theta, then when you encounter this, where you still have a plus jb, same complex number, but this time it appears in the denominator, then its angle is still theta with a minus sign ahead of theta, okay? Now, that is exactly what we have here, okay? Since I already know from this equality the ratio of omega c versus omega n, then I can substitute this result into this, and this is what I will get, okay? Eventually, after going through all the mathematical details, this is what I have. Or in another way, this. In another word, this, all right? This looks complex on the surface, but let's just plot this curve. That is this curve of damping ratio versus phase margin. How do I determine phase margin? I determine phase margin based on the definition of phase margin. What is the definition of phase margins? I first have to locate the gain crossover frequency. How do I locate the gain crossover frequency? By definition, gain crossover frequency is the frequency where this is true. That is, where the gain of the loop transform function is 1. That is how I determine the gain crossover frequency. Once I determine the gain crossover frequency, all I need to do in the next step is determine how far away the phase of my loop transform function in that gain crossover frequency is away. How far away is it from the minus 80 degree? All right. So nothing fancy. It's all based on the fundamental definitions. All right. This is what I have. What does it tell me? What can I learn from this curve? Okay. For engineers, extract information from figures is a very important skill. Okay. Now it tells you that if you increase the damping ratio, you increase the phase margin. So it tells you that phase margin is directly related to relative stability. Why is that the case? Because we learned it before, okay? When it comes to damping ratio for the second order system, in the time domain, what happens if you increase the damping ratio? The overshoot of the state response of the second order system will become smaller. That is a sign of the further improvement of relative stability. Less overshoot, better relative stability. That is what we see in the time domain. In the frequency domain, you also see that as eta, that is damping ratio, increases, the resonant peak of the system decreases, resonant peak, all right? So that is also an indication that higher damping ratio means better relative stability. Here, since we have such a monotonic relationship between damping ratio and phase margin, we know that large phase margin is good for relative stability. Also, when you look at this curve, instead of just look at it as a one curve, you can actually break the curve into two parts, right? Why do I do that? Because the slope of these two regions of these curves are entirely different, okay? In this region, when the system is under dam, increasing damping ratio drastically increase phase margin. But when the system becomes critically damped or even over damped, that is when the damping ratio has a value larger or equal to 1, increase damping ratio still increase phase margin, still improve phase margin, but the improvement is almost negligible, okay? It's relatively insignificant, all right? Now, so that's how we view this curve. Now, you can plot this curve another around. Here, damping ratio is viewed as independent variable. Phase margin is the dependent variable. That is, when viewing this curve, we see how per phase margin changes with the value of damping ratio. And we can view the same thing from another perspective. That is, we want to know how phase margin, if phase margin increases, how damping ratio changes. And this is what we have. And since this equality is relatively complex, it is difficult for us to directly determine the relationship between eta and phase margin. So some smart people tell us that if the phase margin, if the damping ratio is not too large, all right, this curve can actually be approximated by this blue broken line, whose is actually this blue broken lines is actually a very good linear approximation of these two solid black line, all right? And this blue broken line actually can be represented as eta equal to 0.001 phase margin, which means in this region, damping ratio and phase margin are actually proportional, positively correlated, all right? So that is a very solid evidence to tell us how phase margin impacts stability of the system. Okay. Now, why do they matter? The issue here is that real systems have many kinds of uncertainties. However, based on the definition of phase margin and gain margin, in the beginning, remember that we have these two statements. One, for gain margin, it tolerates changes in system strengths. For phase margin, it tolerates changes in system timing, all right? So these two types of tolerances are important, but they are not everything. Because real systems have many kinds of uncertainties, not just gain changes or phase delays. But nevertheless, PM, phase margin, and gain margin are still good robustness measures. I really like this term, robustness, because when it comes to personality or character of a person, robustness is also a very, very important trait. It means, for example, how I face my failure, okay? When I become very, very frustrated, or I just tell myself that no matter what happened, I can always come back, all right? So robustness is a very important trait for personality trait. Similarly, robustness is also a very important measures for control systems, okay? Now, the thing is, by definition, when it comes to tolerance, phase margin and gain margin seems to be very limited because one deal with gain variations and the other deal with only phase delays, which correspond to time delay. However, even though uncertainties have many sources, their dominant effect near stability boundary is to shift the gain and phase. And gain margin and phase margin tell us how much such shifts occur before the feedback loop become unstable. So these statements tell us exactly why gain margin and phase margin are critically important, because even though on the surface they are limited, but no matter what the certainties really look like, their dominant effect near the stability boundary is still to shift the gain of phase. All right. So if I have a lot of room waiting to be shifted, I don't want to say waiting to be shifted, but never in any event, I will encounter uncertainties. So the true gain margin and true phase margin will not be the same if I have sufficient amount of room to tolerate those variations. Then my system have a good robustness, and that make me sleep well at night. Okay, I wouldn't worry about my system will crash entirely just because there are some small uncertainties that I have not considered when I design the control system. All right, now let's now address the relationship between phase margin and time delay. And from this example, we will know that the impact of time delay on system stabilities. Now, for a time delay, Laplace transform is e to minus st, all right? And if I replace x by j omega, and then to transform my representation to x domain to frequency domain, this is what we'll have. And the magnitude and the angle of this transfer function are given here. As you can see, we already saw this. multiple times. For time delay system, its phase response is minus omega t, okay? And it is a straight line whose slope is t, minus t, all right? Now, let's use a first order system as our first example, okay? In the X domain, the system I'm dealing with is minus XL, 1 plus ST, all right? So this is a first order system whose time constant is T, okay? Time constant T. The larger the time constant, the slower the system, okay? And the time delay in this case is L, okay? Let's see what it really looks like when it comes to frequency response. So what I need to do here, since I want to study phase margin, so I go to the body diagram of the loop transfer function. So let me take the magnitude of the loop transfer function and then take log and then multiply it by 20. And this is what I have. The magnitude of any exponential function is, of course, 1, right? Because based on Euler formula, Ej theta, no matter what theta is always equal to cosine theta plus j sine theta. And if you want to know its magnitude, since this is a complex number, you always take the real square up. You always take the sum of the real part and complex part and then square root it. And since this is always 1, so this is always 1. And if this is 1 after taking log, it is 0. And this is remain what it is, okay? Now, of course, I can, here this term is, of course, 1 plus omega t square root, all right? And our focus here is on the phase response, okay? I have this term, okay? This term, as I addressed in this slide, this is the phase response associated with the time delay L. And this is the phase response of the first order system without time delay, all right? Now, this is the asymptotics of the magnitude plot of our first order system, okay? Now, when it comes to the phase response, we have 2 components. First is this, okay? The first order system, the phase response of the first order system without any time delay. And it looks something like this, all right? And let's assume L is equal to 0.5. And this is the phase response of the time delay system. It does not appear to be a straight line, all right, like this. The reason is that the frequency here is actually log omega, okay? It is easy to tell this is the case because the spacing between these beams are not the same. These points are not equally spaced. And if I add this curve with this curve, what I get is this curve, which is the phase response of the time delay first order system. So the time delay has a very negative effect on system stability because it pushes the phase response curve downward to reach minus 100 degree faster, all right? So by doing that, it actually narrow the gain margin. All right. Let's look at another example to demonstrate why time delay is an inevitable factor in real industry application. Here, what we have here is a metal moving strip passed through a pair of rollers. And the function of this pair of rollers is to compress the moving strip to a desired thickness, all right? And this is what people do in the metal industry, all right? So metals pass through rollers that squeeze it is thinner, right, and to a desired thickness. Now, a sensor, which is located here, downstream measure the thickness. And controller compare the measured thickness to the desired thickness and commands the motor to adjust the roller force, right? Because the sensor is located at some distance d away from the roller, where the real action is, we get a transport delay. And that transport delay is, of course, this. D is the distance, V is the moving velocity of the metal, of the moving strip, all right? And let's say this is the transfer function of controller. This is the transfer function of the process to be controlled. And we have a time delay. And the time delay is, when it comes to phase shift, is this. And its phase response can be plotted as a function of omega. And as we saw this before, okay, it will decreases. I'm sorry, we never saw this picture before. Okay, we saw another picture. Okay, here, the black solid line represents the system without any time delay. Okay, so by definition, this is gain phase margin, and this is gain margin. But because of time delay, this curve, due to time delay, the real phase response shifted to this curve, all right? So because the magnitude part remain the same, so the gain crossover frequency is still the same. But when you inspect the phase response, this red curve compared the original black curve is much closer to minus 180 degrees. Therefore, the phase motion changes from this to this, which means phase margin is considerably smaller than its original values. And the impact is not just limited to phase motion. Okay, the negative, such a negative impact would also appear in gain margin because now my phase response decreases faster than what it was, all right? So it will reach the minus 80 degree faster, which means its phase crossover frequency is lower than what it was, okay? And originally, this is the phase crossover frequency, and this is the corresponding gain margin. And due to the time delay, my phase crossover frequency becomes smaller. And as a consequence, my gain margin will also become smaller, which again is an unfavorable result for system stability, all right? Now, this is another example of time delay. Here, we have a water tank label control system, okay? I use, here, this is the block diagram for this system. This is the dynamics of the tank. This is time delay. This is the dynamic of the actuator, hydraulic actuator, which is used to control the openness of the valve. And here, I have a flow, which is a sensor, help me to determine the height of the tank. All right, that is this number of H. All right. Now remember, in this diagram, this diagram tells you one thing that we have to always remember. That is, actuator as well as our sensor, they are subsystems. They always has their own dynamics. All right, because when water surface increases or decreases, the flow will fluctuate a while before it settles down, right? Same thing happened to actuator. When you turn on the actuator, it does not reach its maximum of its default output immediately. Okay, it would take the actuator a while before it can fully respond the demand of the input. All right, okay, keep that in mind. All right, so this is the system. Okay, now here is the body parts of this system. This is static curves for the magnetic part of the body diagram. Okay, and these are the phase responses without time delay and with time delay. Okay, as you can see, the phase margin drop, but about, I think, 15 degrees. All right, because original it is, this angle here is minus 20 something. Here is almost minus 40. Now, these two angles are still well above minus as 80 degrees. So the system is still comfortably stable, even with such a time delay. But nevertheless, the time delay compromises the phase margin. It decreases the phase margin. It makes the gain margin smaller. So time delay is always an unfavorable factor for system stability. All right, let's switch our attention to another very special system, which we call non-mini phase systems. Now, we know a transfer function usually is represented as a ratio of two polynomials. For this polynomial, we call it characteristic equation. And the roots of the characteristic equation are the poles of the systems. And we know the location of the poles matters. Is if any one of the poles is located on the right-hand side of the S-plane, then the system is asymptotically stable. On the other hand, if all the poles are located in the left-hand side region of the S-plane, then the system is asymptotically stable. And we can go even one step further, okay? If you move the pole leftward, deeper into the left-hand side of the S-plane, then the speed response of the system will become faster, all right? So the reason why we know this is because we spend a lot of time in understanding the impacts of the poles, okay? We know which poles are stable poles, which poles are unstable poles. However, we never study the impacts of the location of zeros. Actually, it also matters, okay? Now, here we have two first order systems. they all have the same pulse. Excuse me, I really need to drink some water. Okay, very, very thirsty. Okay. However, there is one major difference between these two systems. They have the same pulse, but they have different zero. Okay, the magnitude of the zero, that is distance between the zeros and the imaginary axis, is the same. However, for this system, this zero is located on the left-hand side of the x-plane. And this, for this system, its pole is located in the opposite side of the x-plane. Now, Planck's function having neither pole or zero in the right-hand x-plane are minimum phase transfer function. So this is a minimum phase transfer function system, where those having poles and or zeros in the right-hand side, right-hand x-planes are non-minimum phase transfer function. Okay, now the focus here is on the zero. That is, we can divide zero into stable zero or unstable zero, depending on which side of the x-plane the zero is located. All right, so we don't want to discuss. We don't. There is no need to discuss the unstable poles because its pole is located on the left-hand side. Is no luck. Okay, everything will crash. Now, the focus here is on unstable zero. What's its impact, if anything? Okay. Now, this is you also did this slide before. It demonstrates you how you establish asymptotics for sample poles. Okay, this is the amplitude spectrum and phase spectrum of a sample pole. Now, similarly, we can determine the asymptotics for the magnitude plot, amplitude spectrum, and the phase spectrum for a sample stable zero. Okay, here we assume zero is stable. Okay, now for a non-minimum phase system that has a right half plane zero, which is forced the system to introduce extra phase lag. This is the phase lag introduced by the unstable zero. By comparison, if I have a stable zero, the phase response is this. This is not phase lag. This is phase lead, right? Because the phase angle it introduces is all positive. All positive. By contrast, for the stable pole, the phase angle is all negative. All right, but if zero is, if what we are dealing is an unstable zero, then this is phase response, as you can see, is all negative. Okay, for example, let's compare the phase response of these two systems, which has the same poles and similar zero locations, but one is stable zero, the other is unstable zeros. Okay, this is the phase response of this. This is the phase response of this system, which has an unstable zero. As you can see, the phase lag effect introduced by the unstable zero. Okay, so which means for by introducing an unstable zero, the phase curves of the Luther's function will go faster to reach, to go faster, will move faster downward to 100 minus degree, and which it apparently will decrease the phase margin. And apparently, it will make this curve go downward much, much faster. For example, originally, this is what it was, and it can become something like this, okay? And the phase margin will therefore become smaller. Okay, so unstable zero is not good for stability. Okay, I will explain more in the later part of this course. But one critical problem of non-mean phase system is this is the pattern of its response. This is the state response of a non-mean phase systems. Typically, for a first order or second order system, its state response looks for a first order system, its state response looks like this. For a second order system, it's a little bit more complex. If it is an overdamped system, it will look something like this. If it is an underdamped system, it will look something like this. All right? But for non-mean phase system, it will move in the initial phase of the response. It will move in the opposite direction before it come back to the right direction. And this can cause a lot of problems because, for example, what you do is to raise the temperature. But once you initialize your control system, the temperature in the beginning will actually go lower. Okay, and that's not something we want to see. Let's say you want to move your autonomous vehicle forward. If it is non-mean phase system, then that autonomous vehicle will actually move backwards first before it going forward. And that can cause a great problem because in the back of your car, there is a person sitting there, okay? There is a boy, girls sitting there. Oh, the car will hit something, okay? And that is not desirable, okay? So non-mean phase system is really an issue and that really a problem. And we want to avoid such a system if we can, all right? Okay, okay. So a few minutes left, okay? Now, before 11 o'clock. Now, here, for the remaining time of this class, I need your cooperation. But if you are willing to, it's a request. It's not a demand. Okay. If you don't want to do it, you don't have to do it. This is a request from our school. This is a QR code. You have by scanning this QR code, you can enter a survey system to evaluate your response to English teaching class. It has nothing to do with the teaching quality of this instructor, okay? At least that is what I was told, okay? It is just a survey how our school to determine how students think about courses teaching in English, okay? So for the remaining few minutes, I'll just leave you to finish this survey. Okay. Again, it's not mandatory. If you don't want to do it, don't do it. Okay. Okay. It's a request. It's not a demand. All right. I'll come back 10 after 11. All right. Thank you very much. Okay. 这个观点啊，谢谢。